This is a huge discovery, and we think that it's a huge discovery. The most exciting piece of this telescope, of this remarkable instrument we've put in space, is finding things that we didn't expect and can't explain, because that means we have to revise our understanding of the universe. The Big Bang Theory is the pinnacle of cosmic theory that explains our origins, but the James Webb Space Telescope, JWST, has found something that completely goes against it. Neil deGrasse Tyson has said that the Webb Telescope saw black holes of a previous universe that created our universe. It might be time for our cosmic understanding to be rewritten again, but how much will the changes be? Join us as we explore the JWST discoveries, which make no sense at all to astronomers. Could they have been wrong about the Big Bang, or was there a mistake with the measurements? Let's find out. JWST found extremely early galaxies. Over the past century, one of the most significant scientific triumphs has been the formulation of the hot Big Bang theory. This theory supposes that the universe as we perceive it today emerged from a state that was hotter, denser, and more uniform. Initially suggested as a credible alternative to mainstream explanations for the expanding universe, the theory gained astonishing confirmation in the 1960s with the discovery of the primeval fireball, now recognized as the cosmic microwave background. For more than 50 years, the Big Bang has stood as the preeminent theory explaining our cosmic origins, with an inflationary period happening before it and setting up the events. However, both cosmic inflation and the Big Bang have faced persistent challenges from astronomers and astrophysicists throughout the years, and the JWST has found yet another challenge. JWST introduced a new layer of complexity to the cosmic narrative. Its detection of early galaxies unexpectedly more massive than anticipated threatens to reshape our comprehension of the universe. The JWST revelation of these high-mass galaxies in the early universe suggests a potential need to reevaluate our understanding of the cosmological framework. This discovery does not seamlessly align with existing astronomical models. The James Webb Space Telescope has only been operational for less than 2 years, but it has already provided unparalleled glimpses of the universe during the first few 100 million years after the Big Bang. The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe. One notable revelation has been the unexpectedly quick emergence of large star-studded galaxies. Utilizing the JWST's infrared sensing instruments, astronomers have pinpointed 6 colossal galaxies from the universe's infancy. These entities, if their magnitude is confirmed, possess the potential to reshape our perception of galaxy origins. Published in the journal Nature, these findings rely on data collected by the James Webb Space Telescope, depicting the universe as it existed 13.5 billion years ago, which is a mere 3% of its current age. So what is it about these galaxies that's so confusing? A mere 500 to 700 million years after the colossal event that marked the birth of our universe, something baffling unfolded. Galaxies displaying a level of maturity similar to our 13-billion-year-old Milky Way. In these celestial entities, the mass of stars reaches several billion times that of our Sun, with one potential behemoth boasting a staggering 100 billion times the Sun's mass. To put it in perspective, our Milky Way harbors a star mass equivalent to around 60 billion suns. In other words, these galaxies are more massive than our own Milky Way. Astrophysicist Erica Nelson from the University of Colorado Boulder, co-author of the study, conveyed her astonishment, stating that it's bewildering for entities of such magnitude to show up so quickly. The conventional understanding didn't anticipate the swift formation of galaxies with stellar masses matching those of the Milky Way in the early years of the universe. The unexpected revelation challenges prevailing cosmological theories, which suggest galaxies evolve from small stellar and dust clusters gradually growing in size over time. According to this narrative, matter in the early universe coalesced at a gradual pace. However, this narrative falls short in explaining the newfound colossal entities. This revelation defies established scientific beliefs and disrupts the conventional wisdom that the universe's colossal galaxies took a considerably longer time to develop. Astronomers describe these entities as universe breakers, a term coined informally, noting that they are indeed living up to their name by challenging and reshaping our understanding of cosmic evolution. Astrophysicist Emma Chapman from the University of Nottingham in England, uninvolved in the study, suggests that if these findings withstand scrutiny, our perception of the early universe might undergo a seismic shift. The revelation of colossal galaxies in close proximity to the Big Bang challenges the notion of a dark cosmic era, suggesting that star formation could have been going on much earlier than we thought. However, before we start rewriting the annals of cosmology, a note of caution emerges from the researchers. The possibility lingers that some of these entities might be concealed in supermassive black holes. What appears as starlight in the images might, in fact, be gas and dust succumbing to their gravitational pull. Another astronomer unaffiliated with the study points out that the intricacies of black hole formation and growth during these early years remain shrouded in mystery. She says that the data introduces not a contradiction to cosmology, but rather a call for understanding the novel physics governing their formation and expansion. To validate their discoveries, researchers could employ spectroscopy to capture a spectrum image of these identified objects, shedding light on their age. Galaxies from the early universe exhibit significant redshift, indicating that the light they emit has undergone considerable stretching on its journey to Earth. The higher the redshift value, the more the light has stretched, signaling greater distance and age for the galaxy. Spectroscopy could unveil whether these potential galaxies, labeled high redshift candidates, are as ancient as they appear or if they are intrinsically recent galaxies from a more recent cosmic period. Astronomers emphasize the need for more observations to confirm the findings, but they suggest that regardless of the outcome, the identified mass implies a staggering revelation. The known mass of stars during this cosmic era might be up to 100 times greater than previously estimated. Even if the sample size is halved, Michael Bonasek from the University of Texas Austin adopts a different perspective on the issue. Unveiling his insights in Nature Astronomy, the prevailing cosmological model labeled lambda CDM, with CDM representing cold dark matter, posits a scenario where ordinary matter and dark matter were thoroughly mixed during the early universe. As dark matter halos collapsed to give rise to the first galaxies, a portion of the intertwined ordinary matter transitioned into new stars. This cosmic dance of matter, both dark and ordinary, played a crucial role in shaping the early universe. Understanding this process is key to deciphering the formation of galaxies and the intricate evolution of cosmic structures. The formation of dark matter halos was a fundamental step in the evolution of the universe. These halos are regions where dark matter is densely packed, and their gravitational pull attracts ordinary matter, primarily hydrogen and helium. Within these regions, the conditions become ripe for the birth of stars. The process of star formation in these dense regions of ordinary matter is what eventually leads to the formation of galaxies. Bonasek and astrophysicist at the University of Texas Austin, has been at the forefront of researching the early universe and the distribution of matter. Bonasek emphasizes that our understanding of the early universe has been significantly informed by the cosmic microwave background radiation. The cosmic microwave background radiation is the afterglow of the Big Bang, a relic radiation that provides a snapshot of the universe when it was just 380,000 years old. It offers a wealth of information about the distribution of both dark matter and ordinary matter in the early universe. The cosmic microwave background radiation is like a time capsule, allowing us to peer into the past and understand the conditions that prevailed shortly after the Big Bang. It shows a universe that was remarkably uniform but with tiny fluctuations in density. These fluctuations are the seeds from which galaxies would eventually grow. The regions with slightly higher density would over time attract more matter due to their stronger gravitational pull, leading to the formation of dark matter halos and subsequently galaxies. Bonasek's research involved calculating the proportion of ordinary matter that should have transitioned into stars to account for the high-mass galaxies detected by the James Webb Space Telescope. The JWST has revolutionized our understanding of the early universe by providing unprecedented observations of galaxies that formed in the first few 100 million years after the Big Bang. These observations have revealed galaxies that are much more massive than previously thought possible at such an early stage in the universe's history. The key question Bonasek sought to answer was how these massive galaxies could form so quickly after the Big Bang. The conventional understanding of galaxy formation suggests that galaxies grow gradually over time as smaller structures merge and accrete more matter. However, the JWST findings challenged this view by showing that some galaxies attain significant mass very early on. To address this, Bonesick embarked on a rigorous analysis to determine the efficiency of star formation in the early universe. He calculated the fraction of ordinary matter that needed to be converted into stars to produce the observed mass of these early galaxies. The results were startling. Bonesick concluded that nearly every available atom of ordinary matter would have had to be used in star formation to match the mass of the galaxies observed by the JWST. This near 100% efficiency of star formation is extraordinarily high and suggests that our current models of galaxy formation may need to be revised. The efficiency of star formation in the modern universe is much lower, typically around 10%. This discrepancy raises several intriguing questions. How could star formation have been so efficient in the early universe? What mechanisms drove this rapid and efficient conversion of ordinary matter into stars? And what does this mean for our broader understanding of cosmology and galaxy evolution? One possibility is that the conditions in the early universe were fundamentally different, allowing for more efficient star formation. The higher density of matter and the more intense gravitational interactions could have led to rapid collapse in star formation. Additionally, the lack of metals, elements heavier than hydrogen and helium, in the early universe might have influenced the cooling and collapse of gas clouds, facilitating more efficient star formation. Another consideration is the role of feedback processes. In the modern universe, star formation is regulated by various feedback mechanisms, such as supernova explosions and radiation from young stars, which can heat and disperse the surrounding gas, preventing it from collapsing to form new stars. In the early universe, these feedback processes might have been less effective or operated differently, allowing more gas to collapse and form stars. Bonesick's findings also prompt a reevaluation of the dark matter component in the early universe. Dark matter does not interact with electromagnetic forces, and thus does not emit, absorb, or reflect light, making it invisible and detectable only through gravitational effects. It plays a crucial role in the formation of cosmic structures by providing the gravitational scaffolding around which ordinary matter can gather and form stars and galaxies. The efficient conversion of ordinary matter into stars in the early universe suggests that dark matter halos might have been more massive or more effective at concentrating matter than previously thought. This new understanding of star formation efficiency has broader implications for cosmology. If star formation was indeed so efficient in the early universe, it could impact our estimates of the total amount of ordinary matter and the formation history of galaxies. It might also influence our understanding of the reionization era, a period when the first stars and galaxies ionized the neutral hydrogen gas that filled the universe, making it transparent to ultraviolet light. One intriguing aspect of Bonesick's research is the possibility that some of the light observed from these early galaxies might be misattributed. The light we see from these galaxies is not just from stars but could also be from accretion disks around supermassive black holes. These accretion disks emit a significant amount of radiation, which could contribute to the overall brightness and apparent mass of the galaxies. If this is the case, it could mean that the actual star formation efficiency was lower than calculated, with the remainder of the mass being in the form of black holes and their accretion disks. This consideration ties into the broader puzzle of how supermassive black holes formed so early in the universe. Observations have revealed the presence of supermassive black holes with masses of millions to billions of times that of the Sun within the first billion years after the Big Bang. The formation and growth of these black holes are still not fully understood, and their presence in early galaxies adds another layer of complexity to the story of cosmic evolution. Bonesick's work underscores the importance of continued observations and theoretical work to refine our understanding of the early universe. The JWST, with its powerful infrared capabilities, is poised to provide more detailed observations of these early galaxies, helping to resolve some of the outstanding questions. Additionally, advances in numerical simulations and theoretical modeling will be crucial in exploring the various scenarios for star formation and galaxy evolution in the early universe. Bonesick's research highlights the significant challenge posed by the JWST discovery of massive early galaxies to our understanding of cosmology. The near 100% efficiency of star formation required to explain these galaxies suggests that the early universe operated under different conditions than we currently understand. This finding prompts a reevaluation of our models of galaxy formation and the role of dark matter and ordinary matter in the early universe. As we continue to probe the cosmos with advanced telescopes and refine our theoretical models, we move closer to unraveling the mysteries of our universe's origins and evolution. Yet, Bonasek deems this near 100% efficiency as bordering on the impossible. He says that the modern universe has about a 10% efficiency in comparison. Mark Velayer from MIT, who wasn't involved in the study, says the paper's theoretical analysis is very sound. The calculation robustness stems from minimal assumptions, according to Velayer. Despite Bonasek's computations, does this imply the overthrowing of lambda CDM? He stops short of dismissing lambda CDM. He says that no other theory currently matches its capability, making it a last resort to contemplate replacing it with something else. But what alternative explanations could be in play? Leading a team from the University of Minnesota, Haley Williams unveiled the discovery of a captivating early galaxy in merely 500 million years post-Big Bang. Also relying on the JWST, the galaxy's faint visibility hinges on gravitational lensing amplification. Williams highlights its star formation rate, which is tens of times higher than galaxies from a slightly later era. While acknowledging the lower mass of this galaxy compared to those scrutinized by Bonasek, Williams speculates on the potential applicability of this intense star formation to higher mass galaxies at similar redshifts. However, Bonasek remains cautious, considering the small size of this object, just 105 light-years across, significantly smaller than typical galaxies. He contemplates the possibility that it might be a globular cluster instead. Addressing the tension in cosmological models, one alternative involves adjustments to lambda CDM. Early dark energy models, or ED-propos, modify the behavior of dark energy immediately after the Big Bang. This adjustment could reconcile discrepancies related to the Hubble constant to align with other observations. These models require extra matter to be present in the early universe. Bonasek calculates that in such a scenario, the density of matter in early galaxies would triple, diminishing the need for hyper-efficient star formation to achieve comparable outcomes. However, ED models contend that the universe is only 13 billion years old, a massive difference from the 13.7 billion number gained from other measurements. Another plausible resolution revolves around astronomers potentially misattributing some of the galaxy's light to stars. Bonasek leans toward the likelihood that the light originates from accretion disks encircling supermassive black holes. Considering this one of the most plausible scenarios, astronomers, having glimpsed a handful of these galaxies so far, caution that their presence in a mere quarter-millionth of the sky may not be representative of the entire cosmos. Joel Ledger from Penn State University comments that we're seeing such a small patch that we might miss out on the bigger picture. Bonasek emphasizes the urgency to scrutinize additional data before making definitive statements, admitting that, in some respects, the universe defies comprehension.